So my name is Aude Billard. I'm a full professor at the School of Engineering at the University of EPFL, which is the Swiss Institute of Technology located in Lausanne. My plan is to give a little bit of an overview of some of the work that we did in my group for the past 15 years, which is a long journey through theoretical work as well as experimental work in robotics. So we're interested in getting robots to be able to manipulate objects similarly to the dexterity that we see in humans. So very much interested in having robots being able to pick up objects, catch them in flight when they fly, or drop them skillfully, trash things, move things very rapidly, pick up any type of object and manipulate them in the hand. So all of this dexterity is still lacking in robots for two reasons. One is that they tend to not move fast enough. Not just the motor, it's more the intelligence behind it, which is still very slow. So we are really, all the work that we do in my lab is to endow them with an intelligence that reacts within milliseconds at the real speed of their computer, much faster than a human brain. Another thing that we are working on is to have them being able to predict things ahead of time very rapidly so as to react appropriately. So there are applications for manipulating objects in your hand. There are applications also for safe navigation of robots among humans. We're seeing more and more robots being deployed in our environment. Think of a wheelchair, which can now become autonomous. It becomes a robot which is carrying a person from A to B. That wheelchair is going to drive on pedestrian lanes. And so that wheelchair becomes a little bit like a vehicle. The difference between the wheelchair vehicle and a human being is that the wheelchair is usually a very hard body and the human body is a very soft body. So if for some reason in a crowd you have a contact between the two, you want the contact to be very soft. You want the wheelchair to absorb most of the energy so that the pedestrian is not hurt. So a lot of the work that we do is on controlling also for this, what we call the compliance, how soft and how not soft you want the robot to be. There are cases, conversely, when you want a robot not to be soft. Typically, when you want a robot to catch something in flight, it needs to be super fast and super rigid to catch the thing on time. Yeah, so it's not just me. So everybody in robotics those days are really trying to get robots out there. By out there, we mean not in a secluded environment where everything is pre-programmed. For a very long time, we used to think that we had to design the environment for robots. It was the other way around, like we design roads for cars, we design our environment for things that we were designing. So it was a sort of a closed-loop system, and now we are in an approach where we think that the thing we design need to be designed to mingle well with the natural environment. Now, by natural environment, we think of us as humans. So if they come out of the factory, and by factory we have to understand a factory meant only for robots. So they can still be in a factory, but in a factory out of their cells. They used to be secluded in cells. So they may be working side by side with human workers in the factory. That's the first thing that we're going to see. That's the first thing we actually already see, partly. Not you, me, but people working in a factory. They do see machines interacting with them more and more. And then we have the last step, which is to have robots really working in our daily environment, be it in our street, in our homes, or simply robots working for us in, when you take a flight, when you take a plane, it's almost a robot. When you take a metro, a train, those days, they are robots. The doors open and close just based on a sensor. All of this is roboticized or automatized. So those systems, they're already slowly in our daily environment. But they hardly move, or they move only on tracks. But the next step would be a robot that really move. And yes, they can work in healthcare. They can also move on you. They can be prosthesis that you wear that is attached to one of your limb. They have then to adapt to your body, but they have also not injure. They should not endanger you, but they should not endanger other people either. So this has become really the holy grail for all of robotics those days, and my lab contributes to this. So I used to work on all of it for a long time. Actually, when I did my PhD here in Edinburgh, I built robots did the programming, the low programming, built the actual body of the robot, then the control system, then the actual software, all of it. The thesis was more about the software, of course, because this is where you have scientific novelty more than the hardware, but the hardware was there and necessary to demonstrate that your software can do something useful. Unfortunately, over the years, we've moved a little bit away from building hardware ourselves, and we are now more dependent on purchasing hardware outside. So we focus much more on the software and the algorithms behind that and the mathematics behind it. Yes and no. That's the interesting part. I was actually giving another talk about 2 weeks ago at IRAS, telling people exactly this. Don't be surprised if you go back to the literature, read what's been published more in the 80s and 90s, not as far back as the 70s, but 80s, 90s, most of the concepts that we see nowadays in research in robotics were already discussed at the time. So is it because we don't do any progress? No. I think it's because robotics is very hard, because it depends so much on the hardware, on redesigning things that have been designed by evolution for millenniums. And we are trying to do that in a few decades. So designing a good hardware and designing a good control system and to have them hand in hand work in a very complex environment remains challenging. But indeed, things like balancing a pole, being able to control accurately for force and position, once you have something that is an external object, is still a topic of research in robotics. We have seen huge advances, and we're still seeing that there are things that are difficult to solve. Let's take the example of pole balancing. The difficulty of the pole balancing is that it's an unstable system by design. So first you had to design the mathematics behind this to prove that it was unstable. Once you had satisfied yourself to see that it was an unstable point, the question was, how could you stabilize it? And the trick is that when you hold a pole, you have to keep moving because it's unstable. So you have to always bring yourself back to this equilibrium point. Now, how do you know that is the equilibrium point? Well, you have to track it. To track it means you have to have a sensor. Then we go back to hardware. How precisely can we know where we are? We, as a human, when we think we're moving our hand, we are very imprecise. We have to use our eyes to know where the hand is exactly. And then this with respect to our body. It's the same for robots. They're a little bit more precise to know where the hand is, but to sense forces that are applied here and to sense the displacement of an object is still a challenge, especially because you have to do it within milliseconds. You have to be incredibly fast. As soon as your pole starts tilting one side or the other, you have just a few milliseconds to react before it falls. Before it's too late, you cannot just move it to bring it back up. So this challenge to be able to perceive things accurately, very rapidly, is still an issue for robotics. Once we will have solved that, I think the world will be open for robots to really be deployed. I did my undergraduate, bachelor, and master in physics with a specialization in particle physics, which I did at the European Center of Nuclear Research at the CERN. And the interesting part is that during my master's thesis, I was given a new algorithm. It was supposed to be something, an alternative to the usual statistical approach to read out the outputs of so maybe I should explain what the CERN is. So at the CERN, you have particles colliding with one another, and that allows you to start deciphering how many particles do you have to exist. You have to discover new particles. The way that this analysis is done is based on statistical tools, very advanced one. When I was a master student, my professor came to me and said, look, there is a new tool that is an alternative to the other statistical method. Do you want to try it? It's called a neural network. I was intrigued. I used it for my master thesis. And even though the neural network theory at the time was developed by physicists primarily, I hadn't been taught what a neural network was, because it was brand new. I was curious to understand more the technique, and I wanted to continue studying for a master or a PhD. I was very, very interested in AI, which was really the beginning of it. I applied for a scholarship, which I got, to go to the MIT, but it allowed me to go to two different places, two Departments of Informatics. There was the Department of Informatics at the University of Edinburgh and the one at the MIT. I had a choice. I could go to the both of them. I decided to go to Edinburgh. I thought it would be a very beautiful city to visit, and that's how I ended up here. I did a master in knowledge-based system for a little bit more than 8 months, and because I had high grades, it was converted into the first 6 months of PhD, and then I went on to continue with a PhD here. How did I got into robotics? During my master in Edinburgh, there was one class taught by John Hallam, which actually taught us about reinforcement learning, and that class also had a practice session. Practice session was to control a wheelbase robot to be able to never get stuck anywhere. And that was fantastic. It was the first time that I was actually building something that was moving. So I did that with a friend of mine. We designed a robot. I built a controller. And it was a competition. We probably worked 40 hours a week in addition to the rest of the master. We won the competition, but more than that, I think at that time, robotics won. I mean, we were just, it was just so great to see things happening. You know, in physics, you study the world. You try to explain the world, but that's all what you do, and you're one person among many, especially if you work in nuclear research. When you do robotics at the time, you were doing everything. That's why I said earlier on, I missed not being able to both build a robot and do the control system, because we could do everything. So it's a little bit like creating another being. Maybe I shouldn't say that. It's a little bit the same. Like you create a child, and then you help the child grow up. And you create a robot, you create a body, and then you create a brain, and then you see it evolve. It was fascinating. Then I wanted to. I was set to do an academic career, and I was fortunate enough that I was offered 2 postdocs. One was in Tokyo, and one was in Los Angeles. And I thought, again, earthquake both ways, but one is sunny, so let's go to Los Angeles. I went there. I did a postdoc for a year, then I became a faculty member, and after about 3 years. I was brought back to Switzerland because there was a program to bring people back when they were doing well. So it was called the brain drain program. So they were trying to bring back some of their brains to become faculty members. So I got a very nice endowment, and I became a professor at the university at EPFL. And I've been there since then. So I went back in 2003. I truly believe that we have a little bit of an issue in robotics those days. We've received too much money, shall I say that? There is just too much being published, and as a result, I'm not too sure that progress is as fast as we think, because there is so much being published that it's become very difficult to read everything. And so knowledge is based on knowing what other people do. When I started my studies, it was easy to know what everybody was doing in the world. It wouldn't take that long to read, and you would know about every single group and every single thing they were doing. It's no longer the case, so ultimately when you cannot know what everybody is doing, you duplicate. It's good and bad. It's good in the sense that if you duplicate research, you're sure that whatever is being developed is correct because it's being duplicated, so it's one way of proving that it's correct. But that would be okay if people were aware that they were duplicating, which is not necessarily the case. They don't necessarily compare. So I'm a little worried. I think we need to slow down, perhaps, and be able to publish a little less, but that's a different question. Now, the challenge that scientifically that I'm most interested in myself, and also think that in robotics we should pay more attention to, is how to bridge 2 different trends that have been working side by side for a long time and now start to be bridged, but only by a few number of people. You have machine learning, or AI in general, that is an entire field of its own. And then you have what we call control theory. Control theory is absolutely needed. That's the way that you can characterize the behavior of your system. Yet, without AI, it's not going to solve most of the problem that we discussed before, which is how to get robots out in the world, because the world cannot be completely explicitly represented as it's done in control theory. Control theory is based on building explicit model and explaining the world, which is like physics. But it takes a long time to build all that model. AI is faster, can build approximation of the world. But we need the two fields to really meet more frequently. We ought to have people really being trained in both of them very well, so that we can have guarantees. We go back to the safety of pedestrians, so the safety of people wearing prosthesis. This is only if you merge the two fields that you're going to be able to solve these challenges. So I'd like to see more of that, and this is the reason why we focus in my group mostly now on actual mathematics, the mathematics of AI and control theory together. Other thing that I like to see are robots that can continuously learn. It was framed first by Sebastian Thrun at least 20 years ago, but we still see very little of that. We don't see robots that can learn and relearn and learn from experience all the time, really being deployed. Nowadays, when they learn, it's mostly in simulation. We learn a very good control system, and then we transfer it onto the robot. Or we do it on board, but for only one small behavior. This applies to my research as well. What I would love to see is a robot that does the same as a human being. Go from learning simple things to learning more complex ones, etc., never stopping to learn from the very same program that adapts and acquires more and more knowledge. Many people have tried doing that. Many people still try, but we haven't solved that. This, to me, would be also a game changer. Oh, the University of Edinburgh has always been very strong, and it has continued being strong. No, it's viewed as being very strong. It's viewed as being very strong theoretically, as well as experimentally. You have one of the best robots, humanoid robot, with incredible, superb developments being done on that humanoid robot, which is very far from being easy. You have to be able to control that robot in torque, the balancing, very fast motion. So I don't know, I can speak only favorably of all the progress I've seen so far. I'm a mom, essentially. I have 3 children, and so it's wonderful to have time to be with them. So that's what I do. I play with them. I create things with them. I just happily watch them grow.